I'm Miko Pawlikowski, and this is HockeyStick. Today, we're taking a deep dive into kernels and operating systems, where they come from, their history and their evolution. We're covering classic OSes, as well as virtualization, containers, and Unikernels. I'm joined by two experts. Ian Eyberg, the CEO at nanoVM, a firm specializing in Unikernels and a multiple patent holder, and Sachin Kamboj, PhD, University of Delaware, expert in Kubernetes and Linux containers. Welcome to this episode, and please enjoy. Hello, guys.
Yeah, thanks for having us.
I'll just do one correction. I'm an expert at breaking things, but nothing else beyond that.
I prepared 3 questions for you. And for each of them, you've got a different objectives. You can cooperate, and whoever wins gets the most points, which don't count for anything. So, let's start. Which sentence of the 3 is true? Sentence A. About 4.3 billion years ago, as the Earth cooled and turned from a burning ball of gas into a rock, the first simple life forms started emerging. Somewhere in that primordial soup, unaware of its future success, was the great ancestor of Unix, which millions of years later, in various forms, would roam the earth and whose descendants would dominate their ecosystem completely. Sentence B. In Greek mythology, Prometheus is one of the titans and a god of fire. Prometheus is best known for defying the Olympian gods by stealing Unix from them to give it to the mortals. His eternal punishment includes getting his liver eaten by an eagle every single day. Sentence C. Unix is a family of multitasking, multi-user computer operating systems that derive from the original AT&T Unix, whose development started in 1962. At the Bell Labs Research Center by Ken Thompson, Dennis Ritchie, and others.
Oh man, definitely either A or B. C is too boring to be true.
Okay, so you have to agree on the answer. Which one is it? A, B, or C?
I might have to agree with Sachin here. As they say in JavaScript land, it's more truthy.
All right, so you eliminated option C. Option A or B it is then.
I think I like the Prometheus story and the liver more than scientific facts about Earth cooling and primordial soups. So I think I'll go with the Greek mythology one, even though we all know what the answer is. But yeah, my answer is B. Lock it in.
Yes, I indeed did make up some mistakes in the Unix one, so I would accept either option A or B. All right, question number 2. Which quote from Dennis Ritchie is made up? Quote A. Unix is basically a simple operating system, but you have to be a genius to understand the simplicity. Option B. For infrastructure technology, C will be hard to displace. Option C. The number one benefit of information technology is that it empowers people to do what they want to do. Which one of these is made up?
I'll go with number 1.
Okay, Sachin?
I would say number C, or number 3.
Yes, that was a quote from Steve Ballmer, not Dennis Ritchie. Well done. All right, and the last question then for you. Which Linux distribution did I just make up? Option A, Rocky Linux. Option B, Chrome OS. Option C, Ubuntu Cinnamon. Option D, Debian TV.
Well, there's no Debian TV, so...
There you go.
Perhaps we should do a reality show on Debian TV and call it This Is Our Calling.
Reality on Debian TV. Very well done. You got 3,000 points and you both win. Congratulations.
Hey.
You've earned it. All right, so where should we start? At the beginning of the primordial soup, where at the beginning of time there was Unix? What's the best place to start talking about kernels and operating systems?
Should we start by even before then and what are operating systems and what's a kernel and why are we even talking about that? Or do we just assume that everyone knows that and everyone is an expert on that?
What is a kernel, Sachin?
I guess I first need to get into what is an operating system before I do that. The way I think about an operating system is it serves two functions. The first one is to manage all the hardware and software resources of a computer. And the second one is to provide an interface to the higher layers of software. I think of an operating system as those two functions. I don't know, what's a good analogy for that? A kernel is basically the core of the operating system that does these two functions. The way I think of a kernel is something that runs in kernel space as opposed to user space, but I don't know if that's an accurate description or not.
I think that's pretty accurate. You need something to broker access to the various pieces of hardware that you're using. Even if it's a virtual machine, you still have a handful of drivers, like you want to talk to the network or something. Not everybody can whip out a TCP/IP stack on demand. That's how we subdivide it.
My first question when I looked at that was like, okay, so this seems to be starting in the early 1970s. So what would happen before that? Would everybody have to whip out their own TCP/IP stack? Was TCP/IP invented
TCP/IP
in
did not
1970?
exist.
So it was all custom before that.
You have to figure out what happened before Unix. And before that, computers were so expensive. And we're talking about mainframes here and supercomputers. And they were really tasked with doing one job and doing it relatively well. So the operating systems of the previous years were really designed for batch processing jobs. I need to compute a whole bunch of census data, or I need to compute this data on this many tapes. And all I'm doing is I'm basically loading a bunch of tapes, running this algorithm, completing it, and then going on to the next task. And again, this is way before any of us were born. I'm all talking about hearsay here. But that used to be the operating systems of the past were mostly dealing with tape storage and data crunching and really expensive machines. Most of the operating systems at that time were written as either machine code or assembly. Actually, fun fact, the first version of Unix was also written in assembly. It was rewritten in C, I think. I'm thinking 1973, if my data is correct.
No C to write it in, so they had to. Same for the C compiler.
Oh yeah, even before then, pre-Unix and so forth, there wasn't really a lot of market demand for having kind of a general purpose system like that to begin with, because people were so conditioned to buying these machines to do whatever task they had. And they weren't really thinking, oh, I want to do lots of different things on it by different vendors, especially. That was one thing that kind of shaped how machines and the systems that they ran before worked.
Oh, that's actually a very good point. One of the things that you talk about, typically when you bought a computer, you bought an integrated stack. If you think that Apple today is a walled garden and you're buying a fully integrated system like your own Mac OS and the operating system and the computer is all controlled by Apple, think of it as if you bought an IBM or a DEC computer, the hardware, the software, and everything that ran on it, all the peripherals, they were made by one company. And that was the company that you bought the machine on. So they basically wrote the operating system for that. I think the story of Unix itself goes back to the PDP-7, and it was just like, from what I've heard, it was lying in a corner somewhere where it wasn't really being used, and they wanted to play a game for it. That's how they started programming it. And it was mostly an accident that it happened. They worked on it, and then at that point in time, it was like, we're selling these big, expensive computers. Who cares about software? And software as a distinct entity did not exist. So I think one of the key things is like the first versions of Unix actually came with the source code to it. If my notes are right, they didn't actually release them into the world until I think the fourth edition was written in C, which was around 1973. And then it actually went outside into the world around 1978 or 1979 or so. And it came with the full source code to it.
So who are these people? Because to me, they're like half myth, half legend. Who are they? The researchers? Are they delivering commercial solutions as well? They're just chilling there and inventing stuff. What's happening there?
Yeah, I think you have to go back during that time. So this is like late 60s, early 70s when Ken Thompson, Dennis Ritchie, people like that were working on it. back then it was common for bigger companies to have larger R&D labs. That is not the case today. Like even today, if you look at Google's Project X labs, they're just nuking that entire organization. But back then, like it was pretty common that if you were a Boeing or a Bell or somebody like that, you would have this massive R&D apparatus. And that's partly because it was still coming out of the Cold War R&D era. That's that environment that it comes from. And a lot of these guys, they did wind up at Google starting in 2000 and so forth. So that's like where you get languages go and stuff, and Russ Cox and all those guys.
I think the other thing we have to remember at that time, AT&T was still a monopoly. And being
Yeah,
a
it wasn't
monopoly,
until
they
the
were
early 80s. So
really profitable, making a shit ton of money. And one place to spend it was like, look at all the fancy research that we do.
So does it exist today? Or is it the Nokia labs at the moment? What do they do today? Are they still inventing stuff?
when it existed back then, it's gone through so many different transitions. The breakup in the early 80s split it up into 6 or 7 different regional mini bells. And then different BUs have been bought and sold and rebranded a ton of different times. I think it was the late 90s and the early 2000s when a lot of those people did start migrating to other companies such as Google. So all the guys who were working on Plan 9 wound up there.
So why is everything basically tracking back to Unix? Is it because they got it right the first time? Is it because it was the only real thing that was out there in the open? Why Unix? Why not something else?
I think people vastly underestimate the amount of work that goes into an operating system. If you look at today's world, server environment, forget mobile or anything, but just look at server. There's really only 2 real dominant players, and that's obviously Linux, and then you have Windows that's leeching off of like Active Directory and stuff like that. All that is still heavily prevalent in most Fortune 500s. But yeah, both of those, you can trace their lineage, not Unix, but like their lineage back into the early 90s. And so it's just an immense amount of work to provide something.
So what does Unix actually bring us? If we were to compare like a modern Linux to Unix, which bits would be similar? Which were the ones that they got right the first time?
I'm not sure they got anything right the first time, and I'm not sure anybody ever gets anything right in software. There's a Unix haters handbook, and it's a fascinating read, and it's hilarious because it tells you where people made a lot of mistakes and did that. But I think the end story is the people who worked on this, just to be clear, I would say they're geniuses and they're some of the smartest people you'd ever meet. So it's not that I'm deriding them or saying that they didn't get anything. I think they got a lot of things right. There are a lot of important ideas that came out of Unix and that were copied and used for a while. But I think it's just that the systems that we're building now are so much more complex, and there's so many cases and that were unimaginable when they started out. So it's actually incredible that these systems have survived something like, 50 years now, which is mind-blowing. It's actually a really fascinating history. What are the key concepts that you think Unix was really good at? I think one of the ones that comes to mind is the whole idea behind everything as a file. And just giving everything a file interface had some nice things about the way you can program things that I thought was key. I think if we're not talking about kernels, if we're talking about operating systems in general, I think the whole idea behind having individual programs that do one thing, do it well, but combining it together and piping the data from one to the other was a very interesting choice of things that wasn't possible at one point in time. I think there are a few key concepts that they got really well, but I think one of the key things that happened around that time was this idea of multiprocessing or multiprogramming becoming a thing. And eventually we've gone to where we used to have one processor to having multiple processors and multiple cores. And now we're dealing with something like even a standard computer that you buy off the shelf now has 64 cores, which is, you're talking about supercomputer territory in the 1970s or something like that. So I think a lot has changed.
I'm recording this on a MacBook that runs macOS, which has some BSD lineage.
I have a OBSD from 2001, 2002, somewhere around that point. There was a few years where FreeBSD didn't really have great SMP support. in the early 2000s. And so a lot of users dropped off during that time period. Obviously, macOS is more or less stolen from the BSDs, and then they layered on all the other stuff from Cupertino.
What's the relationship between the original BSD, the Berkeley software distribution, and Unix itself? Why was it started?
Berkeley wanted something that they could use for free.
The reason it's called BSD, Berkeley Software Distribution, is that the first version that was released with Bill Joy was using the exact same Unix source code. So it was literally Unix from Bell Labs. They added programs like Ed and ROF and a few other things, and that's what they called the distribution. The distribution was actually software on it, but the kernel was still the Unix kernel. Eventually, it came to the point where AT&T was like, wait, software is a thing. We can make money off this, and we need to protect our intellectual property and be fancy about it. So at that point in time, I think they started with, okay, we'll have to rewrite some of this. And that's where they actually started rewriting quite a bunch of the code and made sure that they did it in a way that they would not actually copy any of the original code and be completely independent. And Bell Labs did end up selling the intellectual property that was Unix. The funny thing was they actually sold the trademark and sold the source code separately to 2 different companies or something like that. And I believe Novell actually ended up suing the University of Berkeley and saying that you own our copyrights. And the case was actually settled in Berkeley in BSD's favor, except for, I think, 3 actual files that they said was infringing their copyright. And those 3 files ended up being rewritten. And then the agreement was that Novell or whatever who owned those copyrights would agree that they don't own any other code in the BSDs. And then you can use BSDs without infringing on anybody's copyrights and anybody's intellectual property. So yeah, that's a little history as I understand it. BSD originally started out with the actual Unix code. It was rewritten for that. I think the biggest reason why BSD became so popular was not just that it had the code and the utilities on top of it. I think the biggest reason BSD became so popular was because it had an implementation of the TCP/IP stack that was spectacular and more performant than the official version that people were working with. So that's where a lot of people started using it, especially with, I think, BSD 4.4, which was huge. I think the internet and Unix goes hand in hand, and the story behind that, mainly because of TCP/IP.
Do you know the story FreeBSD and Net and then OpenBSD? Why the split?
FreeBSD and NetBSD were made concurrently. They took the BSD code and started working on it. Think of them as almost like distributions of Linux, just that instead of using the same kernel, they forked off the same base and then started developing them independently. OpenBSD is really interesting. So the NetBSD, the idea behind that was mainly portability. They wanted to support the largest number of architectures, and one of the things they did was they had a clear demarcation between this is machine-dependent code and this is machine-independent, and being able to define these are the parts that need to speak to specific CPU architectures, and these are like the completely independent ones. I think the key idea behind OpenBSD, I think it's called W or X, or it's either writable or executable, and the idea behind memory or management was that certain pages would only be writable or certain pages would only be executable. So they did a huge ton of hardening in order to create OpenBSD.
OpenBSD's always been years ahead, especially in terms of Linux when it comes to security. They were the first to do redirects. They were the first to do ASLR. They were the first to do lots of things, ROP gadget mitigation, everything, to a degree that they're willing to completely destroy user space and like break it, which Linus is famous for. Like, we don't kill user space. They've always had that stance, and they've had the stance of screw you, security is more important. It's one of those things where it makes it hard to bring it into a normal corporate prod environment because of that reason. But at the same time, they are the trailblazers when it comes to things like that.
People would argue that they have some really good implementations of certain things that Linux is lacking.
I'll just name it right now. Pledge and Unveil, for instance. Linux still is complete crap when it comes to locking things down. SE Linux is just not usable. It's really poorly designed. It's not finely scoped. I don't think Legend and Unveil is like the right answer, but it's a lot better than SE Linux or in some of the other LSMs that exist today.
I think for the benefit of other people who might have a vague idea, and as they read about and use Linux or whatever they're using, they see a bunch of standards or like acronyms that might not necessarily make a lot of sense. I know that for myself, I'm still a little bit fuzzy of what's part of POSIX and what's not. Do you know where this actually come from and what POSIX actually means in practice, for example?
It comes from the open group. It's a set of standards. And really, this goes back to the Unix wars of the early 90s. We like briefly mentioned it. In the early 90s, you had all these corporate vendors with their own proprietary versions of Unix. And so this is actually the birth of Linux, by the way. And so they're all suing each other. They're all saying, hey, you're infringing on my stuff and that's mine, not yours. And so that was actually one driving reason behind Linus in 92, 93 when he releases Linux, because there really wasn't a quote like free, unencumbered Linux. You had GNU going on forever with a lot of the user land, but not an actual kernel. And so that was a major reason. Obviously, with Tannenbaum, he had Minix, which was a teaching operating system, which Linus basically took that and as like a rough draft and went to town on.
What other acronyms are there? There's ELF, the executable and linkable format. Was that part of Unix as well? Or is that
so like
just a calculator?
A.out used to be the predominant format, say in the 90s, and there's different formats for different systems that people would use, but ELF is actually a relatively newer format if we're talking about the decades here. A.out, which is still in use on, say, FreeBSD, for instance, can still use that.
And how is ELF related to ABI?
It's more of breaking up the binary into different sections. When you have a program, there's lots of other things that are going on. Your program is probably not just one binary. More than like 99% of the programs out there are going to be dynamically linked to a handful of libraries, in particularly libc. You're going to have a whole bunch of other stuff like libnss for DNS and maybe your Instagram, so you use libmagic or whatever. So you have all these different libraries, and somehow the program has to know how to load that and link it in the proper spot too. So we know where all the symbols are. If I make a call to a function, I know where to actually address that function. And then there's also page permissions and things like that. Different parts that are marked, as we mentioned earlier, different parts can be read, write, execute. It's analogous to user permissions, but it's a different concept. We're really talking about parts of memory that have these functions. And it's actually something that's showing up again when we talk about WASM, because WASM doesn't have any of this.
And what's GNU, you said? I've always pronounced that new. I'm realizing now. So, well, we've got a certain Stallman who appears in the picture, and he likes recursive acronyms. Yeah, GNU's not Unix, and that's very hipster. What's GNU?
We're really tracing back to the FSF, Free Software Foundation. And again, it goes back to the fact that a lot of these companies back during that time had proprietary versions of Unix, and you want to use it, you got to pay for it. That just didn't work for broke college students. It didn't work for hobbyists. If I just look back on my own kind of upbringing or whatever, this was the software that we could use. We couldn't just go download some random corporate made software. Whatever was free was what we could have. And also this kind of touches, I think, on this whole like definition of open source today. So you have all these companies that have these BSL licenses and so forth. And some people are getting a little bit crazy too, because they think they have the right to just copy some other code and call it theirs because it's open source. That's not the open source that I grew up with. I'm like 40 now. When I was like, say 12, and I wanted to use Linux to play a game or whatever, what I would run into is I would go find like a Voodoo 3, whatever graphics card, right? And guess what? I would compile on X and the driver would not work because parts of the driver were not there. Like literally the code doesn't exist. That was just not something that they did. Same thing with Win modems. I was on like maybe a 28.8 baud modem and I want to upgrade to a 36K. I'd go out, spend my hard-earned $50 or whatever it was. And guess what? The modem doesn't work because I literally don't have the code for it. It was never about ripping off the modem manufacturer and like rebranding and reselling their code. It was more of, I just want to use the damn product. So that's a big difference between today's like definition of open source and like what open source concerns were back in, say, the mid 90s.
Actually, the fun story, just to reiterate your point, of the way I've heard it is Richard Stallman, before he started GNU, used to work at MIT on one of the labs, and he was working with a printer driver, and the printer driver was buggy, and he was like, let me just fix this, because if something's broken, why don't you fix it? And he was like, wait, I can't fix this because I don't have the source code for this? That's preposterous. Like, how can I not have the source code to fix a bug? So he decided, and I think the biggest thing to come out of GNU was probably the GPL, or the idea behind copyleft. And the whole idea that I'm going to actually use copyright to enforce open source. So the idea is behind the GNU licenses, if you want to distribute any of the binary, you have to distribute the source code with it. That's the idea behind it. And Linux adopted GPL version 2. And that's really a big reason behind its success, I would say. Companies do not like GPL v2 very much because they can never close it up anymore. With FreeBSD or with the BSD style licenses, you can create a closed source version of something if you wanted.
Yeah, so that's why they call them viral licenses, right? Because once you're infected, you can never close it back. So GNU was not, it's a bunch of things, right? It's the GNU compiler, it's a bunch of bin utils, it's a bunch of core utils, it's the glibc, right? And then there's the GNU herd that last time I checked still wasn't finished. Do you think it's ever going to be feature complete?
That's another thing I like to play with back in 2000, 2001. So yeah, the thing is, it's a research toy, right? The core concepts behind it are really interesting. It never really got to the point where people were really using it, not for real purpose. Operating system development is really hard and complicated and takes time. It's not something that a grad student with a semester or two can just like whip out and make something that's production quality.
Andrew Tannenbaum wrote Minix because he wanted to teach his operating system class how to write an operating system. And it was like the best way is to have a working operating system to play with. And people were like so excited. Oh, look, there's operating system and it does this. And I want to add this feature to it. And they were like, hey, here's some code. I want to add this feature and I want to add this feature and I want to add this feature. And he was like, oh, your feature is awesome. I don't have a problem with it. The biggest problem is if I add it to Minix, the operating system becomes more complicated. And now I can no longer teach it in a single semester graduate course. So he was like, no, my primary purpose behind Minix is I want to be able to teach this to people. And if I add all these fancy little features that are very important and awesome and needed, I won't be able to do that. And eventually that was one of the things that Linux was like, oh, you don't have a multi-threaded file system? Are you crazy? Like, that's why it's brain dead? So I'll just make my own. And there was this big flame war between Linus and Andrew Tannenbaum, where Andrew Tannenbaum famously came out and said, Linux is obsolete. And that's actually a fascinating read if you read through that. That's one of my favorites. But I think we're getting back to what's a microkernel or some monolith and things like that.
So wasn't that one of the main accusations that writing a monolithic kernel is silly and he should have done a microkernel?
A lot of that was driven because when you look at some of the domains that Andrew was working in outside of his teaching and some of the systems that really do demand that sort of design, RTOSes, we'll touch on this, and then also a lot of safety critical systems. So think planes, trains, cars, anything that moves fast and weighs tons and can kill you type of thing. So none of that stuff should be running Linux. And it's a good thing that like the F-16s don't run Linux because they would kill a lot more people than they do today. So there's a lot of good things in it, but touching on that design real quick, the whole premise is that instead of having this monolithic kernel that does like everything, and if you find a fault and it just dies, the entire system dies, microkernels basically say, hey, if one system dies, it shouldn't kill like the other part of the system. You could say that Andrew actually won this debate, because if you look at virtualization, I think Rosenblum, who was one of the co-founders of VMware, he said something like virtualization was basically microkernels done right.
So what's your take on why Linux, of all this family tree that we're looking at, why not BSD? Why was it Linux that became the de facto standard for running anything other than trains and planes?
Well, I think if you go back to the first .com boom, late 90s, right up until 2001, basically. Before that, if you wanted to build a stack, say you're some startup or whatever, you either go to Microsoft and you purchase a license, or you go to one of the proprietary Unix vendors, purchase a license. So Sun would be an obvious choice back then. Expensive, both the hardware and the software. And then you had this kind of upstart Linux, which was free. And so that started becoming a much easier choice to make back then. And so they were just
FreeBSD, right?
Yeah, but they were so much further ahead, because if we're saying like it's 99, Linux has been around since 92. You have 7 years of widespread distribution. In particular, Red Hat has been spreading the gospel for 5-6 years. So it's permeated everywhere at that point. Whereas the BSDs, they're still used in academia and so forth. And obviously we have a few companies that are utilizing them for one reason or another, but didn't have that distribution that Linux had at that time. And when that first .com bubble hit, it just exploded.
Okay, so I think we're going to have to take a closer look at Linux and some of the interesting aspects of that. But before we do that, I just wanted to also mention that there is that little thing called Windows that's not shown on this example. I don't actually know all that much of the history of MS-DOS and then the 9X kernels and the NT kernels. I do know that you can actually find MS-DOS source code on GitHub now, which is, in a certain way, funny. Do you know the story of MS-DOS, how it came to be?
Bill wrote a guy a check for it.
Yeah.
That's pretty much what happened.
Basically, he promised IBM that he would have an operating system. Then was like, shit, I don't have an operating system. Where can I get one? Tried to buy one from DEC. The dude he went to ended up like ghosting him and going on a flying tour or something like that, the story goes. So then he went and wrote another check, and basically the original version I think was called QDOS or Quick and Dirty Operating System or something like that. And it was rebranded as Microsoft DOS, and that's where it started. The key thing was you have to remember that you're talking about like the 8086 family of processors, which were like these primitive machines compared to the Unixes that were running. There was a processor, a block of memory, and that's it. They were going to run one thing at a time. There was no kind of multiprocessing, no kind of memory protection. So the whole reason you could take down a system or you had the blue screen of death was there was no distinction between kernel space and user space. You could actually write to the memory addresses in the kernel space, and if you accidentally made a mistake and wrote something, boom, you just crashed your system. I think it used to be the norms all the way until 386 first included the concept of a protected mode. The interesting thing is the Macintosh app came first, and the Macintosh in 1984 blew people's minds away, and Windows tried to copy that, and it was quite horrible until Windows 95 came along. But 95 was still based upon the DOS-based architecture, and there was another kernel that they made, which was Windows NT, which was for companies and server groups and things like that. And the Windows NT is what really morphed into Windows 2000 and the later version of Windows that we use today. I think that's where that kernel lineage goes.
All right, so let's think a little bit now about what's interesting about Linux. What are the features and what are the parts of it that made it such a success? Because it's a hockey stick show, so it would make sense to look at that. What's the killer features? What's unique, or maybe what's the most useful about Linux?
Honestly, in my opinion, just from my own experience, it really comes back to the fact that it was there and it could be used easily. Even today, I still have to buy a license for Windows, right? So that's still a major blocker, especially when you start looking at, if you believe GitHub's quote of 100 million developers in the world. I don't think I believe that, but it's definitely measured in the tens of millions. That's a really big deal.
Okay. But let's give Linux a little bit of credit. It's got some nice features, right? It's a concurrent computing OS. You can have things leveraging multiple cores. What else? It's got a virtual file system, right? That built on top of the concrete implementations, which I think helped. Like on a normal day, you probably don't care what kind of underlying concrete file system you have. We've got virtual memory, right? Memory management and paged virtual memory, which makes things easier from the developer point of view. It's pretty feature complete as well, right? You've got pretty much everything that you need right out of the box. And as we talk about virtualization and containers in a little bit, that's probably also worth mentioning. It's got some interesting async I/O things, right? I think you were telling me about that session.
What you're describing is basically all the features of an operating system or things that an operating system needs to provide. And obviously Linux being one of the most popular ones and being used everywhere has a somewhat unique take on some of those features. Probably the biggest thing going for Linux is portability. Because the source code was open, because there wasn't really one company behind it, there were a lot of people like, oh, I need this. I'm going to come up with this architecture, I'm going to come up with this, and I need an operating system. I can just take the Linux operating system and port it to this new architecture, this new CPU set, and that's an easy way of getting an operating system as opposed to good old days where, if you came up with a new CPU or a new architecture, you would have to write an operating system for it. I think that probably had a huge effect of that. That's not to say NetBSD, for example, or FreeBSD even runs on a lot of different operating systems, but I think that had a huge reason for the success of Linux was the fact that it was open, which meant I could really port it to different operating systems and use it. It's feature complete, and if it wasn't feature complete, somebody would contribute those features to it. Mm-hmm. Having said that, there are a lot of people who would argue that Linux has a huge case of NIH or not invented here syndrome, in the sense that they try to reinvent the wheel and try to do it poorly compared to borrowing from other places and other systems. So one of the things we have right now is containers, and containers are an awesome thing, just that containers are a complete myth. Containers don't exactly exist. There's no concept of a container inside the Linux kernel. You cannot say, give me a container. Containers are made up of namespaces, C groups, capabilities, an overlay file system, and a sprinkling of sauce here and there, but they're not really a nice virtualization technique. Or they're not a construct inside the kernel itself, let's put it that way. Whereas if you look at the BSDs, they had jails, and might be a nicer implementation. I'm not sure if I can really say that, but they had a better way of looking at that.
I think, again, this is one of the things that if you look back in history, you start to understand why it even happened. So obviously, if you want to trace it all the way back, you got Bill Joy coming up with GRoot, right? So that was like before I was even born. So that goes way back. But if you go back to the 2000s, this is where I think containers as we know them really started. And that was because VMware and Google were butting heads a lot on, especially going after employees and so forth. And Google wasn't trying to use any of VMware's software, but they wanted something that was very similar in scope. And so Google started adding a lot of the support to what we know as containers with namespaces and C groups and things of that nature. They were the ones that came in and started adding these features to get what would work for them. Now, keep in mind, they designed it because we're Google, we control everything. and we can use it at our company. They weren't really designing it for the entire world at this point. And so that's where certain technical decisions were made that guys like me might not agree with. But that's only because they weren't designing it for everything. They were just designing it for Google. That's actually a very long history. You'll see these features where something that we've been working on recently called user managed concurrency groups. That's a feature that's been trying to get into mainline Linux for 8 years now. And it comes from Google. But for lots of different reasons, it hasn't been merged in. And it's a very common scenario.
So if we do a quick rundown of the main things, right? You want to be able to contain the file system. So this is the chroot/jails things. You want to be able to control the resources, right? We've got C groups, we've got V1 and V2. Was that also influenced by Google, the C groups addition?
So groot, just to trace that started off because there was a desire to have a separate file system view for especially build artifacts. And then also back when FTP is still regrettably heavily used, but back then that was also a way of isolating different users, incoming folders, and so forth. It was never designed with like security in mind, is what I should say.
But then we should probably do the honorable mention of Docker, that kind of packaged it all together, added the file, the image format, leveraged copy on write type of file system, and became a unicorn, right? With a few billion valuation. Twice.
The first one burnt and crashed. I forgot what year it was, 2018 or 2019, something like that. They basically had to recap the cap table. And so everybody on it was wiped out. They sold off a large part of the enterprise portion to Mirantis, and then decided to refocus solely on the developer, dev, test, desktop sort of experience. And then over the past so many years, now they're a unicorn again. But the first one ended in a fireball.
I missed that bit entirely.
Oh, yeah.
That's very cool. Okay, and then we've got all these other players that looked at it and said, okay, so this is really cool, but it's not that hard to write a runtime, so we want to have our own runtime, right? We've got the Run C, we had a bunch of different projects from places like Red Hat. We had the weirder one like gvisor from Google that was a slightly different approach to that. So who controls the container runtime at the moment? Is that CNCF steering the Run C development? Who's in power there?
As you just mentioned, there's no one runtime to roll them all, right? There's sets of standards that people are supposedly adhering to, but at the end of the day, you can go out and make your own standard. So with that XKCD comment where we have 7 standards, what do? We just go create our own.
Yeah,
exactly.
The incredible thing is Kubernetes came along and killed quite of all the other container orchestration systems. They killed Mesos, for a better term. Docker came up, saw Kubernetes being a thing, decided to build Docker Swarm. That never really took off. So Kubernetes killed them. And as far as Kubernetes is concerned, they have the container runtime interface, and that's all they really care about. So even the containerd does its own things and can manage a lot of different runtimes and support a lot of different features, the only one that Kubernetes really cares about is the container runtime interface. There's obviously CRI-0 or CRI-0. I'm not quite sure what the pronunciation is from what I've heard of it, but that's decided, okay, we're just going to support the runtime interface. So that's like the abstraction layer. And then behind the scenes, Runc is using the Linux constructs and creating containers. And I think there are other people that are doing their own thing. I know there's Firecracker on Amazon that creates a limited set of containers. I know there's like Kata containers, and there are all kinds of fancy stuff. And yeah, as long as you support the CRI interface, Kubernetes is happy, and then what you do behind it is up to you. I'd be interested on your take on this, Ian, and I think Unikernels would fit nicely.
Firecracker and gvisor were basically a response. I don't even want to call it a response because they were created for different purposes, but they're used as a response to the containers don't contain argument. Firecracker basically spins up VMs, so it's more of a replacement for QEMU than it is for Kubernetes. But people like Fly.io use this, and there's a few other companies that are starting to use it outside of Amazon. Firecracker basically trades runtime latency for boot time latency, so they can boot faster because they got rid of some other things that they didn't think that they needed. But the runtime suffers a little performance penalty a little bit. And then gvisor has gone in a couple different directions, and I think they've made improvements since the last time I looked at it. But basically, gvisor also would isolate your program to give it a sandbox layer, so to speak. They used to be using ptrace, but if you have access to actual hardware, you don't need to use that. There's other methods now, which is good because ptrace is incredibly slow in the way it works. I don't know of too many companies that have said that they're really using gvisor outside of Google, but you do see quite a few companies raising their hands around Firecracker now.
So what's Firecracker using to actually run the VMs? Is that KVM under the hood?
Yeah, so it uses KVM the same way QEMU can use KVM, because KVM is the actual hypervisor functionality that Linux has to provide. So it's just like a lightweight Rust interface that talks to KVM. And a kind of a funny tidbit is that they actually stole this from Google. So Google had a project called CrossVM and basically forked that, rebranded it, and produced Firecracker. And now it's taken a life on its own, but it was essentially a project that they just took.
We didn't really mention AWS, so you talked a little bit about the VMware versus Google in that story, but then all of a sudden we got AWS joining the party and trying to make their own mark. What did they do, like with the virtualization?
That's an interesting story because, again, in the mid-2000s, you have VMware that's just starting to get good. VMware's first products were kind of dog shit. It didn't really work very well for the environment, the types of computers that were everywhere. This was like before we had threads, before we had SMP capabilities in commodity machines that existed before, but commodity like your average company. And so it took a few years for VMware to get out of the gate. But 2003, 4, 5, around that time period, that's like when people are just like, oh, this actually starts to make sense. And then just not even a year or two after that, Amazon took Zen from Citrix and they slapped an API on top of it, essentially. And that is what we call the cloud today. It's really just virtualization with an API. That was a major game changer.
Yeah.
I
So at
guess
the
the
end of the
question is,
day-
where's OpenStack and all this?
So
Because
a lot of people think OpenStack's dead, but talk to any telco out there and it seems like almost every major telco still heavily uses OpenStack.
Any alternatives to OpenStack in terms of free to use?
I think it comes down to the size of an installation that you're trying to do. So if you have so much that you really need like APIs and you need a full-blown stack, so like a telco that might have hundreds or thousands of machines running it, that's like where OpenStack might come in. But if you're only like maybe 5 or 10 boxes, maybe a lot of people will use Proxmox or something like that instead.
Yeah.
Which is kind of like a vSphere alternative. It's better to think about like how big of an installation you really have and where it makes sense. And then like
Right.
the whole like, why are you doing your own virtualization layer versus using the cloud? Because there's different decisions there.
So I think the conversation is naturally taking us into the Unikernels and Ian's area of expertise. But before we do that, I learned a few weird words that I'm hoping maybe you can help me give some examples of. There are hybrid kernels and exakernels and multi-kernels and ramp kernels. And I was wondering if you ever heard of any real examples of these things and whether any of that is actually interesting, because it sounded to me like a lot of that was a theoretical, oh, it might be a good idea, but maybe separation kernels made sense to me in like the aviation scope or something like that. Do you have any interesting stories about those?
Separation kernels are definitely still used, specifically with the applications that you mentioned. This kind of dovetails into kind of the formally verified space. So when you're dealing with like aviation and trains and cars and all that sort of stuff, regulations come into play. And so those regulations will sometimes have these really stringent specifications where, hey, this part needs to be formally verified. This needs to be no bugs, yada, yada, yada. You'll see in like a modern day car, there's going to be like many different pieces of software running in a car. And the stuff that's on your heads up display is going to be a completely different system than the one that deals with other controls inside the car. In fact, you can see this play out in real life. There's a guy named Dan who runs this company called Green Hills Software. And so he's sold a lot of this sort of software to DoD and organizations like that for the past 30 years. Just go search him on YouTube. He has all these videos where he bashes Elon Musk and Tesla for putting Linux in their cars. And he actually ran for governor in California just to try to kill Tesla.
I think you bring a very interesting point, which is I had a scary one running Linux because half the time we run into a problem of what does customer support or whatever tell you? Switch it off and switch it back on. And that seems to be our solution to everything. That's not a viable solution if you're driving 70 miles on a highway and you're asked to switch something off and switch something back on. That's just not doable.
Or if you're in a 747, 30,000 feet up in the air, probably don't want to switch that off and on.
And I think the big reason for that is back to the concept of state and to what extent do you understand state and can you reason about it? The idea is when the system first boots and when it comes up, you have some kind of indication of what the state is. What are your variables? What are your bits? What do they look like? But eventually, as you start building more and more, reacting to the world, more and more things happen. System processes are started, processes are stopped, they react to different changes. You eventually end up with a state. And usually when you get a crash of some sort, it's because your system is in a state where you can't really reason about it or you don't know how you got there. And the easiest solution is, instead of working on it, is switch it back off and switch it back on. And I think this tilts back in nicely into Unix. When it came out, it was, I wouldn't say it was designed to be, but it was like, let's build a practical system. Whereas all the research that was happening in the universities at that time was along how to build a correct system. And there was a crazy ton of work that went into how do we detect a deadlock? And can we ensure that there are not going to be any deadlocks? And the whole Unix philosophy was, what's a deadlock? Like, I'm going to be an ostrich, shove my head into the sand and say there's no such thing as a deadlock. And if there's a deadlock, you can just restart it.
I think that's a really interesting contrast to make because there's some systems out there where you can't allocate new memory at runtime. Like it's outlawed. You just can't do it. Whatever memory you need, you have to have it before the system starts. So that's very different than I work in an office and I need a spreadsheet. You know, it's very different system design constraint. And I think it's just what a lot of people are exposed to. It's like a commercial versus a consumer aspect in an analogous way. There's just so many more people working in the office than running a jet or something.
Although I think it's not entirely true that there is no Linux on an airplane, because every time I fly, there seems to be someone's tablet kind of crashes, and then they do this thing when they said, oh, we're going to go and restart it. It's going to take about 15 minutes.
Right.
And then they have to stop everybody's movies in the row. And everybody's looking at you, oh yeah, it's because of you. You're the one with the unlucky tablet. So I'm pretty sure that must be some kind of Android there, right?
Heads-up display versus the avionics.
I'm okay with killing the entertainment every now and then, even though I don't think that's really acceptable. But running Linux on tablets makes sense. Running it on controlling the flaps and the aerofoils of a plane, hell no. Don't try to do that.
So you mentioned Tesla. Do they actually run critical systems on Linux as well?
I would imagine that they definitely have multiple systems. I do know that they do have Linux as a form of something inside, but there's different layers of security or regulation that you have to conform to for different functions when it comes to things like cars.
The other thing that Ian alluded to is a lot of the systems that you run in cars are microcontrollers. And in the case of microcontrollers, when you're coding for them, you don't really have a libc. There's no concept of a library. There's no concept of a malloc. you basically have a fixed set of memory and you decide what each piece of memory is going to be used for and you stick to that. And it's a very different environment to what you might be used to if you're just programming in C on a standard system where you could do a malloc and a free.
glibc just had a heap CVE issued for it that's been in glibc for 20 some odd years now.
I heard that they found a bug in qsort and glibc, which was really incredible. And it was just using the fact that your comparison operator should be transitive, and that's not transitive. You can actually exploit it. The fun thing of how they discovered this was actually somebody was looking through old code from Solaris or something like that, and they were like, this fixes the issue with transitive, with your comparative function not being transitive while sorting. And they were like, oh, that's a thing. And then they were like, oh, glibc still has this bug because they never fixed it there.
Right.
I love the anecdotes like that, especially when it took 20 years to find the bug. Ian, you mentioned twice already that writing an operating system is very hard. So why do you work on Unikernels that basically introduce a new operating system that you're also going to custom compile with all of your applications?
Just to clarify, when I say it's hard, what I mean is it takes a lot of effort. It takes a lot of time. So given enough people and enough time, you can make something. But if it's just one guy toying in his garage on the weekends, it's not going to happen. You really do need to put some resources at it. I work on it mainly because I got sucked into it. I come from the security world, and it was very clear to me coming from the security world what the promise was as compared to like how we do things today and what kind of things that people do to mitigate security concerns today, which to me are just completely worthless. Scanning for a hacked system or scanning for a system that's going to be hacked is just, it's crazy. It's crazy to me. That's like how people do things today. It was very clear that one of the main pain points is that the whole purpose a hacker is trying to break into your system is to run their code on it. It really has nothing to do with your code. That's just how they get into it. They find the hole or they use an exploit. That's just the doorway into the house. That's not why they're at your house to steal your stuff. Yeah. They want to run a crypto miner. They want to dump the database. They want to do something of that nature. And that always involves running at least one, if not many different programs. And that was like one of the things. And it's, we get this performance boost and it makes things easier and yada. That's what drew me into.
Yes, I think it would be helpful if you could just go into a description of what exactly unikernels are, or what your take on unikernels are, and why they're so incredibly useful, or why are they so alluring to it. We've talked about containers a little bit, but we haven't really described like what's the distinction between, let's say, a container and a virtualization and a VM, and what makes unikernels so awesome.
I guess to start off with, I'll say that there's more than a handful of unikernels out there. And they're all extremely different. Some people might think that they're like different distros or something of the same thing. No, they're completely different. Some are focused on performance. Some are focused on security. Some are focused on specific use cases. Like maybe they want to run a 5G stack. There's lots of different reasons why people are looking into this. At least from my perspective, I got interested because of the security side of things. And then I think if you talk to most of our users, I would say 80-90% of them just think they're easier to use. Like one command, you build an image. Second command, you spin it up on Google or Amazon. It takes tens of seconds. It's just easier to use than, say, Kubernetes. That's probably the major reason why our users do that. But to compare and contrast with containers, for instance, so containers under Linux, A, they're running under Linux, but B, say you have 5 containers or whatever. So again, in security, last week, there was a container breakout. Again, what that means is somebody was able to escape the container. And once they do that, they can do whatever the hell they want on that host system, including attacking other containers, because now they're in that control domain. One of the really big problems from a security point of view that I have with Kubernetes is that it extrapolates this management control system from one host over many different hosts. So if you do this container breakout, not only do you have access to that one instance that you're on, you probably have access to the entire freaking network that Kubernetes spawns on. To me, that's a different security threat model than having, say, one Linux VM and another Linux VM. Because sure, maybe I find something where I can break out into the hypervisor, but it's a very different type of security vulnerability. And it does not happen as much as some people think that it might. If it did, public cloud wouldn't be a thing, because that is public cloud, right? That's why, to me, it's like the gold standard. Virtualization literally has hardware-backed extensions built into the chip to provide this sort of security. So we talked about MMUs earlier. It's the same sort of hardware-backed guarantee, which containers don't have. As soon as you find that exploit, like we did last week, it's fair game. So that's a huge major difference. The other thing is there's lots of other differences, but with the unikernel, essentially what we do is we just bundle the kernel portion with the application into one virtual machine and then spawn it. Like I said, different projects do this very differently. Like Unicraft, you pick the hundreds of different libraries that you want to include. And so they can produce very small images, but then you need that expertise on figuring out which libraries you want. I don't think a lot of developers have the time or the inclination to do that. So we have a different approach where we just load raw ELV binaries, which I think, again, just from our earlier users, I think most people want that as the default. There's lots of different techniques and ways of doing these.
So can you walk us through what happens? I've got, let's say, some code written in ASP hipster and say Go. What needs to happen to that code so that it becomes its own self-contained VM with everything it needs? Because you gave the example of whipping out an TCP/IP stack. That's your problem now. How does that work?
At least for our point of view, we have tooling like ops, which is a build tool. It's open source, ops.city. Essentially, if you're just playing around locally on your laptop, you can do ops run whatever your Go binary is, and it'll basically create a disk image on the fly. And so that disk image will have your binary and then whatever else it needs. If you're on a Mac, that file system is going to have 5 files on it in total, and then it just boots it up instantly. So that's like a local dev mode. But you could do like a ops image create, and it'll create a disk image. You can then upload that to Google or Amazon or any hypervisor, any cloud, and use it as such. When it comes to things like knowing what to include or what not to include, we don't think our users really need extreme specialization, and definitely nobody's really asked for it. Nobody's asking us, hey, can I use LWIP or small TCP? Nobody asks us that. And it's crazy to think that somebody would want that either, because if you look at like LWIP, for instance, which is the networking stack we forked, and it is a complete fork, by the way, we've added so much different support to it that you won't find in the upstream, because it's a dead project. So like, for instance, there's things like IPv6 for DHCP. Why do we have that? Because a customer asked for it. There's support like SYN flooding. If you go use LWIP on savannah.org, the mainline branch, that is totally susceptible to SYN flooding. So any project that uses LWIP out there, I can take you down immediately. SYN flooding is something that was dealt with in 1998. So keep that in mind. There's lots of these little tiny details that you might not think of because it's not something that developers do day to day. So rolling it back to the original question of what do we think you need, don't need, it's a lot more complicated. Some people think that a unikernel is somehow not an operating system. It most definitely is. It's just a different type of architecture of a system. It's not like where we take your application and we just link a couple of things to it. That's not how it works. It's more of we take your application and we put it inside this nice little architecture and then let it do its thing.
Let's say you have an application that does asynchronous I/O and it's using, for the lack of a better thing, they wrote it for Linux, so it's based on epoll. So are you going to actually, do you have an implementation of the epoll system calls, or is that how you're operating on it?
Essentially what you'll find in Nanos, which is our unikernel implementation, is you'll find more or less a lot of the same sort of stuff. So I don't want to say we have a one-to-one ePull implementation because ePull is actually pretty large and there's lots of like random flags and stuff. So
That's
we might
what I
not
was going
have
to ask.
every
Like,
single flag. So
do you actually implement the ePull bugs in your
right.
your code?
Like there could be like one shot, there can be edge triggered, there can be
Exactly.
like there's ePull is actually like a beast. It's one reason why earlier on it got a lot of flack compared to KQ from BSD. There might be not a one-to-one thing, and we deal with it whenever it comes up. But the cool thing is there's a lot of software that uses ePull, right? Because we have so many people using it, like bugs show up, they get fixed. A lot of people are bewildered that Linux doesn't really have a default test suite. There's test projects out there, but Linux, the project doesn't really have its own fully functional test suite. It boggles people's minds when they hear this. But the answer is like, well, Linux is, go look at the Git tree. There's like thousands of commits every single day. They get to that because it's just heavily in use.
So are your clients primarily driven by the security aspect of that?
No. So early on, again, coming from that world, I thought that would be a big driver when I found out that a lot of security buyers, they're not the ones that would actually use this software. Our users are SREs, sysadmins, DevOps, random developers, like people day to day using. And so they're not really a buyer, like a security buyer. They're buying stuff for their SOC. And so the scanning software, it's a completely different buying experience. Most of our users, again, are using it because they just find it easier. Like they have a service that they want to put up. We have a lot of Rust users, for instance, and they build the Rust image, they spin it up and boom, like it's working. They don't have to mess with Kubernetes. They don't have to do anything. It just sits there and works. I think ease of use is a major driver for us today. That used to be a main complaint for Unikernels was they weren't easy to use.
Is the performance a major consideration? What's the real world difference between compiling the same code and running this as a container versus running as a unikernel? Yeah, in terms of, for example, your clients moving onto your platform, do they see a savings in terms of actual dollars? What do they see in that respect?
It depends upon which user is using what. If it's like a single developer type of thing, the ease of use is definitely a huge driver for them. It just saves them time. A lot of the DevOps toil, if you will, just goes out the window because again, like you can't SSH into these things. You can't sudo apt-get install whatever you want, which accidentally installs some random library, which introduces a vulnerability, which goes on, right? A lot of that just goes out the window. And it has that kind of encapsulation that containers bring, but it doesn't have all the kind of toil that comes with that. We do have some bigger clients that do have much larger installations. And so for them, security can be an issue depending on who's using it. It really depends on the type of user. People haven't really dived deep into the performance aspects of it yet, but I would expect that to be a thing in the future.
So can you use that out of the box? I know you said Kubernetes is terrible, and there are many reasons you can agree with that. A little bit of an overkill for a lot of people. But can you just plug that as a replacement for a container runtime there?
It depends. I would say there's a surprisingly large amount of software that does just run out of the box, like literally ops run my program. So your Go example is a perfect example. If you have Go or Rust or something like that, it's almost a guarantee it's going to run out of the box. Where it gets more complicated is say you're using Python and some hot new ML framework, for instance. Okay, so how do we build that application? These applications, say it's some Python ML framework, the actual program that we're running is the Python interpreter. And then there's like probably a gig worth of crap that this application has, right? And so these are like random shared libraries, entire folders filled with Python code that I don't know what it does. You have the models that it pulls down. Those are tens of megabytes or hundreds of megabytes in size. So these things can be big, right? And what you'll find is, especially in Python and Ruby, people have implemented convenience commands. So they run some command, but that spawns like 5 different interpreters that each run their own command. And so in cases like that, we do have to go in and we have to figure out, okay, what's the final invocation that they're trying to run? What's the actual program that they're running here? Because it calls like 5 different calls to Python or whatever. And so in that case, we'll either throw in a patch or we'll figure what that is. And then we'll create what we call a package, which is essentially everything that we know we want on the file system. Arguments, the environment variables, that's another thing that gets done is a bunch of environment vars will get set and you don't really know what they are. And then whatever they're trying to run, we'll create that package and then we'll give that to the user and they can use that instead. So that's like probably those cases. A very extreme case is Postgres. So Postgres is one of those System 5 IPC poster child type of situations. It makes use of everything that we don't like in Unikernels. It has multiple processes. Huge offender number one, it has shared memory. So shared memory exists. In almost all cases, it means like you have 2 processes talking to each other. It has semaphores to signal amongst different processes. It has a lot of stuff. It basically was a re-implementation of Ingress from the early 80s, around the time I was born. And then in the 90s, it got rebirthed for the 5th time as Postgres, still using the exact same sort of programming scheme. So anyways, that's an example of something that's actually really difficult to port. But guess what? We ported it. So like now we have a multi-threaded Postgres, which didn't exist before. This is a topic that actually came up on the Postgres mailing list. Again, I guess it's been debated before, but last year there was another kind of debate about, hey, we should do a multi-threaded Postgres because now there's all these different Postgres vendors and all of them, a lot of the vendors are basically saying, okay, it's 2024, threads are obviously faster, obviously cheaper than running processes, and their customers have very large data sets. So processes get really crappy if you start getting heaps of like 30 gigs and stuff, and you have to fork that. Now it starts taking time. Multiprocessing doesn't scale very well, especially once you get like high memory usage.
What's the uptake? What's the kind of market penetration of Unikernels at the moment? I know about the Fly.io, but they're small potatoes still.
Fly uses Firecracker. They don't do Unikernels today. So Firecracker and the proponents of Firecracker will throw out micro VM as a term. And essentially, it's just a container that runs in Firecracker. They're not the only platform player out there that's doing that. There's a few others, like Railway, I think, is one of them, and some others. I think outside of those platforms, Firecracker still doesn't have a ton of stuff. Obviously, Unikernels are way less than Firecracker. One thing I'll throw out there is that you can run Unikernels inside Firecracker because, again, Firecracker is just the machine monitor. It's the host layer. It's not the guest layer. But yeah, we have our users, our customers. There's a few other Unikernel implementations out there that people use. But by and large, I think it's still very hidden from your average developer. You might see some comments on Hacker News where people were like, what's the state of this? But the reality is we have stats on like people who come to our page and then people who click download. So like it's surprising to see what a large difference that is, put it that way.
So where do you see it going? Do you think there's a niche where the Unikernels are just going to dominate? Is that something that is going to stay niche? What will have to happen for it to get like a wider adoption?
In terms of like widespread adoption, I think there's certain trends that push it to more adoption. Like some people think that you have to just have a complete huge category to win. And I don't know if I really agree with that. I'm happy with having enough of a ecosystem and a space to play in. But yeah, obviously security is a huge driving force. Cost, you hear about cloud reappropriation and so forth nowadays. What is it? DHH with Basecamp, he's all talking about screw the cloud. So there's a little bit of that sentiment going around, at least here in the US. The economy combined with tech in general going through a downturn, I think that's going to put a lot of pressure on costs. So cost is going to come into view as well. There's lots of different like non-technical trends that converge that can help push adoption. Our focus has always been to make it as dead simple as possible, to the extent that we made like 2 desktop clients last year, one for Mac and one for Windows, to where like we don't even expect users to jump into a shell.
So there's one thing that I would like you to clarify, because when you got a bunch of containers, you've paid for a VM typically, right? And then inside of that, you've got a certain amount of resources, and you're going to be able to a certain extent for these resources to be shared between the containers. And this is often cited as a kind of cost-saving effect. Obviously, there is the side effect of that if they all try to use that resource, they won't be able to, and they're going to get killed and restarted. For a unikernel, it's going to have an allocated static amount of resources because it's a VM like the other one. So does it mean that you're relying on the VM hypervisor ways of saving the resources, like the ballooning and stuff like that? Or is there anything more advanced that you can do when you've got like the small VMs with unikernels with single processes?
I think it's just a different way of thinking at the end of the day. So yeah, people will bring up like bin packing. We're like, oh, I can stuff all these containers on one host and so forth. What we try to challenge people to do is think about what resources does your application actually need. If you have a website that needs 20 containers, but you're on, I don't know, 2x large or whatever, does it make sense to have 20 containers? So that's the thinking that we throw out there. If you have an EC2 small that can withstand all this traffic because it's just a little Go web server, maybe that's all you need. Maybe you don't need 20 different services. And so part of this comes from, I guess, all the way back in 2014, 2015, where people start pushing microservices and so forth. Some people took that as a cue to carve up what could be one app into like many different things for scalability reasons. But we push back a little bit on that and say, hey, like maybe this should only be using one VM to begin with, and therefore maybe it should only be one app. Now, if you hit RAM limit or CPU limit or whatever, then sure, throw it behind a load balancer, or maybe you have a language that does threads or whatever, and you can vertically scale. That's like how we respond to that. If that makes sense.
It does, although it doesn't help with from my experience, it's very hard to get people to agree that they need amount of resource, because they somehow expect to be able to spike and get these resources when they need them, and then not have them and not pay for them when they're not.
Yeah, on that note, Ops, for instance, has support to deploy these things into auto-scaling groups. So if you like that sort of auto-scaling where you start generating errors or you hit a certain expected load, you can set auto-scaling groups to scale dynamically on that. That works on both Amazon and Google.
I think it's one of the arguments where people said Kubernetes is overkill for the vast majority of people. And if you did have auto-scaling groups, you can't do it. And to the extent in which, yes, you are running on a hypervisor, but you can over-provision resources on a hypervisor. So there's really nothing stopping you from doing that. Now, as long as you're only paying the cost for the resources that you're actually using and not paying for the entire thing that you've reserved, that's fine. Or at least in my opinion, that's fine. So it's just how are you paying for it, and are you right provisioned for whatever you're trying to do?
Yeah.
So is there an inflection, a hockey stick moment for unikernels, where suddenly something clicks and all of a sudden the adoption goes way higher? Is there anything like that you can think of?
Well, like I said, there's these other non-technical trends at play. And I think one of those might be what actually pushes things forward. Some people like to talk about this, what do you call it, killer app. I don't believe in that. I think that's a naive way to put things, because honestly, we already have killer apps, right? That's not the situation. There needs to be a lot of awareness. That's still very low. And B, there needs to be that non-technical trend, which I've talked about, where enough people start linking those two together.
To a certain extent, I also wonder to what I believe computer scientists or programmers or developers are like huge fashionistas, and they always try to run to whatever the latest fashion trend is. So if Google starts doing like containerization or starts doing Kubernetes, everybody wants to do Kubernetes. If Amazon or one of the big cloud providers says, we want to do X, and this is the way we're going to run our own systems, everybody wants to run their system. So if eventually you just need one of the big cloud providers to say, oh yeah, we're going to support native virtualization, and this is the way we're running our systems. And I think it might be that everybody starts doing it at point in time.
Yeah. And I think that can happen too, by the way. Some people wonder why we don't have like our own cloud offering type of thing. I have two answers to that. One is like a lot of our users think it's good enough or better than enough on the existing clouds. But B, like I could easily see somebody like Amazon coming in and saying, hey, we're going to tweak this knob here and this knob here, and we're going to make it like an even better environment to run these things in than what exists today. So they've got Lambda, but Lambda has all these limitations. We're going to remove some of these limitations and make a unikernel environment. I could easily see something like that happening.
Did you try to work with some cloud vendors to roll it out as a feature, or some symbiosis?
No cloud vendor is going to design something just for us. We have contacts for lots of the different clouds, and there's different paths that different vendors take. Some of these vendors, they're also responding to what they see as fashion. So like Wasm has a little bit of that fashion, so to speak, today. And you have various vendors creating environments for things like that, or doing different takes on, like Microsoft has their thing coming that they mentioned.
All right, guys. So for anybody who has learned a little bit here and wants to go and discover some more, what kind of resources should we recommend them? Any books, any videos that are worth? We'll put the links in the show notes. We'll definitely put the link to Linux is Obsolete. What else would you recommend to extend this discussion?
If anybody wants to check out the open source tools that we have, nanos.org, which is kernel, and ops.city, which is a build tool. Both of those have extensive documentation and videos, and we have a YouTube channel with a bunch of tutorials and stuff on it. Our tech blog, if you like nitty-gritty kind of technical stuff.
There's another podcast called BSD Now that I think I've learned quite a bit from at times. There's always Wikipedia. As long as you take it with a grain of salt, there's some Wikipedia articles that are really good. FreeBSD comes with the FreeBSD handbook, which is quite amazing. And then there are obviously Linux man pages. So if you're going to use a feature, the first place to check, I know most people would Google it. The manual pages are still really good if you want to look at things and look at what the trade-offs are, or sample code. Quite a lot of manual pages actually come with sample code that you can copy paste and use, so you don't need to go to Stack Overflow. You can go to the source.
And for anybody who wants to maybe learn the basics of operating system designs, is it worth going and playing with Minix? I think they had a recent release, actually.
What I would suggest is most of the books are older and a little bit too verbose, in my opinion. But there's one called S&3 Easy Steps. And I think it's out of, I forgot the researchers' names, but it's out of Wisconsin.
We'll find it.
I found that book to be extremely written and extensive and easy to read.